Welcome back to our lesson practice review, where today we go through Chapter 3, Lesson 6, which is all about polynomials and their multiplicity. So, factored form of a polynomial is very easy to see what the x-intercepts are, because with what we know about the zero product property is that if we set each of these pieces equal to 0, we can kind of solve for what the x-intercept is. So when I see this x plus 3 here, I know that there's going to be an x-intercept at -3, 0. Same thing with this. I know that there's going to be one at 0, 0, and then here I can see that it's going to be an intercept at 2, 0, which we can kind of see in the graph here. Now, this new idea of multiplicity is talking about kind of this exponent here that we see in the equation. So when we see this x plus 3 squared, we notice that it looks like a quadratic when we kind of zoom into it, right? Like it looks like a parabola at that specific point because of that it has a multiplicity of 2, or an exponent of 2. The 0 at x equals 0 has a multiplicity of 3, and so it looks like a cubic function. So when we look at this here, this part right here, we can kind of see that it swoops down like a cubic function. And then since the last one at x equals 2 has a multiplicity of 1, it looks linear as it crosses through the x-axis. And so really, again, we're looking at the exponents in the equation, which tells us what the graph looks like as it crosses through or bounces off of the x-intercepts. So for number 1 through 3, circle whether each statement is always, sometimes, or never true. First, if a 0 has an odd multiplicity, the function passes through the x-axis. And that is going to always be true, because when we have, let's say, power of 1, it's linear. Power of 3 would be cubic. Same thing with 5, 7, 9. It's going to kind of have this cubic looking shape as it passes through, but it definitely always passes through. For number 2, if a 0 has an even multiplicity, the function will bounce off. And that is true, just like a quadratic, power of 2, multiplicity of 2, it's going to bounce off and therefore not go through. We kind of say passes through versus bounces off. Those are opposites. When we do this here, if it has an even multiplicity, it will always bounce off the x-axis. A multiplicity greater than 1 means that the function passes through the x-axis. Well, power of 1 is going to pass through. Power of 2 will bounce off, kind of like a quadratic. Power of 3 is going to be passing through like a cubic function. And so it sometimes passes through, but anytime that it's even, so the numbers greater than 1, 2, 4, 6, 8, and so on, will bounce off, where it's all the odd functions will be passing through. So in this one here, I would say sometimes. Number 4, select all the functions with x-intercepts at -5, 0, 1, 0, and 6, 0. And so what we know about this is that if we're given the x-intercepts, that means in this case, if I plugged in -5, it would make that whole equation 0. And so when I look at, let's say, a here, if I plug in -5, well, that's going to make this -10 on the inside, which doesn't necessarily make the whole equation 0. Same thing with c here, but with b, if I were to plug in -5, well, -5 plus 5 is 0, and then 0 times all this other stuff makes it 0. So I'm really looking for this first one here, which ones have that x plus 5 in it. So I would say that, these two here, or these three, I guess, help make this first intercept correct. Whereas when I look at 1, 0, I need to, when I plug in 1, make the entire equation 0. So I've narrowed it down. My answers are not going to be A or C, but I do know that if I plugged in 1 here, it would become 0, here, and here. Okay, so that one's all good. Now with 6, 0, when I plug in +6, it needs to make the whole thing 0, which, okay, all three of these do indeed work. And so my final answer for these is all three of the answers, B, D, and E. The different exponents don't really change what the x-intercepts are. They just change how the function looks. Is it passing through? Is it bouncing off? Or does it look more like a cubic function? Number 5, here is the graph. Let me zoom out. Here's the graph for the function f of x. Which of the following equations could represent f of x? So when I look at this, a couple things that I notice here is that I have a point here, here, and here. Those intercepts look like they're at -2, 0, and 1. Where the first one here looks like it's a multiplicity of 3 because it's kind of like a cubic function. This one probably looks more linear, so I would say a multiplicity of 1, whereas this last one bounces off and has maybe a multiplicity of 2. And so when I'm looking at the equations over here, I need to have a multiplicity of 2 when it makes the entire equation 0 at 3, my fault. A multiplicity of 3 when -2 makes the entire equation 0. So already, like, I know it's not going to be either of these two because -2 would not make the entire equation 0. So I've already narrowed it down. It's got to be C or D. The other thing is that when -2 makes the entire equation 0, it should have a multiplicity of 3, which really kind of gives me the answer here that C is our correct function. Let's just go through the other two things here. So at 0, 0, it's a multiplicity of 1. That looks good to me here. And when I plug in 1 that makes the entire equation 0, I have a multiplicity of 2. Okay, yes, I think C is the perfect equation for that. Problem 6 through 8, fill in the blanks so that the polynomials will have the behavior shown at each x-intercept. So in this one here, it looks like both of these are going to be bouncing off. That would be at -4, 0, and +3, 0. If they're bouncing off, that means that they're both going to have some sort of even exponent. I usually like to use 2. So I'm going to plug in 2 here. And then also this has to be 3 because that's where my other intercept is at. Again, this could be 2, 4, 6, 8. Doesn't necessarily matter as long as it's even. This one for sure has to be 3 because that's exactly where my intercept is. For number 7, we have a point here that's bouncing off, which makes sense. We have x squared. That looks good already. This one here looks like it's linear. And so I'm going to call this one a multiplicity of 1. And again, we're saying x plus 2 because my intercept is at -2, 0. Number 8, h of x equals all this hunk of junk here. And I have my graph over on the right side. So I wish these were a little bit closer, but we'll deal with it. So what is that? 1, 2, 3, -4. 0 with a multiplicity of 2, -1, 0 with a multiplicity of 1, and 5, 0 with a multiplicity of 2. And so in this one here, I'm going to call this one 4 to represent this part right here. Then I'm going to call the multiplicity of 1, so this has to be 1, which represents this part right here. And then this has to be 5. And so I originally said that the multiplicity was 2, but remember that as long as it's even, 2, 4, 6, 8, it's all going to have that bounce off look in the graph. So I said 2, but really 4 also works here. So I just need this to be 5 so that it makes that the correct x-intercept. Problem 9 through 10, the graph of the function p of x has the following features. It passes through the x-axis at -9 and 0. So -9 and 0, those are my two x-intercepts, and has a multiplicity of 2 at x equals 4. So again, at 4, 0, I have a multiplicity of 4. So when we do that, oh, sorry, it has a multiplicity of 2, my fault. And so when I write the possible factored form of the equation, I could say p of x is equal to x plus 9 So dealt with that, and then x minus 4, and then it says it has a multiplicity of 2, so x minus 4 squared. Number 10, write a different possible factored form equation for p of x. And so I know that this x minus 4 has to stay the same because that has a multiplicity of 2 at x equals 4, but these two can change because there's multiple situations where we pass through at the x-axis. So, I could just change those both to cubed. That would still give me something that passes through, and then x minus 4 still has to be squared because it has a multiplicity of 2. Number 11, this polynomial has a 0 with a multiplicity of at least 1. Do you agree? And explain your thinking. So, has a 0 with a multiplicity of 1. So this is a very important term here, 0, because it does not say x-intercept. If this sentence said x-intercept, I would disagree, because this does not have any x-intercepts. But remember that we can get a 0 that is imaginary, which means that it doesn't actually cross the x-intercept. And so we could have a situation where we have some sort of 0, like x equals 2i, and that has a multiplicity of 1 that doesn't cross the x-axis. And so in this situation, I would agree because it says 0, because a 0 is not necessarily the same thing as an x-intercept. All right, our spiral review, we're writing the end behavior of each function. So we need to think back and understand that when we have a positive, looks like it's positive leading coefficient, and my highest exponent as a power of 2, that means that the right side points up, and then my end behavior is going to be the same for both the left and the right side. And since they are going up forever, positive infinity and positive infinity. For number 13, we have a negative leading coefficient. Since it's a negative function and then the highest exponent is odd, so the negative means that my right side points down, and since my degree is odd, that these point in opposite directions. So as x approaches negative infinity, looks like I'm going up towards positive infinity. As x approaches positive infinity, looks like I'm going down towards negative infinity. H of x is, I'm looking for the highest exponent term, which is power of 6. So it's even, and that leading coefficient is negative, meaning my right side points down. And since the exponent is even, that means both the left and right side both point in the same direction, which both of them are pointing down towards negative infinity. That wraps up our lesson 6, which talks about multiplicity, and hopefully we're getting better at understanding polynomial graphs. See you on the next one.